As we have learnt earlier, and I have mentioned in the next class before this one, that we are going to today talk about how to find surface area of a parametrized surface. Again, I want to recall what is the meaning of parameterization, that every surface that you see may not be the graph of some function, it may not be immediate, but it might be easier to write it in the follows. So, if you have a domain D in R2, right, then, and if S is the surface, if I denote the surface as S, then the S should be, if S can be written as phi of D, where phi is a map from D to R3, then this phi is called a parametrization of S. So, the idea is this, that here is the domain D in 2 dimensions, which we have already discussed earlier and also have drawn pictures. And if this is a kind of surface, then if you take a point here, say it is uv, it get maps onto some point phi of uv in R3. So, it takes uv is taken to a point phi of uv, where phi of uv is actually these 3 coordinates x uv, y of uv and z of uv. So, this is how we represent. Now, in attempt to compute the surface area, we would try to imitate what we have done for the graph, for the surface which is given by the graph of a function. But we have to understand that it is not easy to find surface area of everything. Suppose if you take a surface area, parameterized surface area, but it is like this, which folds upon itself, like the graph that we had drawn when we were talking about parameterization of surfaces. Finding surface area of such things are slightly difficult. So, that needs to, we need to talk about orientation and all sort of stuff. So, we are not going to talk about those right away. So, here we will consider those kind of parameterization where there the surface itself does not fold onto itself, and it can maybe at the boundaries of D, but we over D it is a surface, but we do not know to what function is its graph. It may be a graph of a function, may not be a graph of a function. So, we are taking a very general view that we will talk about such surfaces which does not fold it into itself, means for every, for a given x there can be 2 y's, we will not have that sort of situation. Given xy there can be 2 z's, sorry. So, given xy there can be 2 z's, we will not have that situation. So, but still we will write it in terms of a parameter in the parametric form rather than writing it as a graph of function, and we may not know we may not know whether at all it is a graph of any function. So, how do I find something like that? So, here I have to keep in mind the surface, right, cannot overlap itself. This is something very important thing that we have to keep in mind. Surface cannot overlap itself. So, once these things are kept in mind, the surface area, which we write area of S, is given as integral over the domain D, the norm of phi of u, and you know what's phi of u, cross phi of v into du dv. Now, we will make a convention that if I take any matrix M, so if I take a M is n cross n matrix, of course, you might ask me how do you get this, we will get to that. Then we will, for short we will write, then we will write determinant of M, we will write like this. You might be thinking why is he trying to change symbols at this moment, but okay, it is just for shorthand that we will use here. And you know, when you give a talk, you can change your notations a bit while you go along, because people are going along with you, while in a book a uniformity has to be maintained. So, if I write a book on this, then we maintain a uniformity, but they are anyway good books, I do not have to toil for that. So, let me see. Now, it is interesting that if you look at the structure, if you look at the norm of phi u cross means the cross product of phi v, these vectors, we have already, what is this? This turns out to be a very interesting kind of expression. The expression that it turns out to be is the determinant of the Jacobian matrix del yz, you know what is this, del uv square of that plus determinant of del xz del uv square of that plus the determinant of del xy del uv, take the determinant and square the value. It looks very surprising, but how such a thing happens here. Okay. So, first let us try to figure out what is this, why it is like this, and then we will try to argue why we are writing, why the area of S is given by this integral, and then one example we can do within our allotted time. So, let me just go and write down what is phi uv. So, your phi uv is x uv I vector plus y uv j vector plus z uv k vector. Now, when you write del phi u, you are essentially looking at the derivatives like this, del u of x uv. I am not writing uv, I am assuming that you understand, just for short I am doing this, del y of u j vector plus del z of u k vector. Similarly, you know what is phi v is a vector of partial derivative, is a gradient basically, kind of, is not a gradient, but some sense, in the sense that basically this actually symbolizes that you take the partial derivative of this, partial derivative of this and partial derivative of this and form a vector in terms of u, and that is phi u. And del x of, so del x of del v I vector, del y of del v j vector, del z of del v k vector. Okay. Now, once you have these notations with you, you know that what is the cross product. Let us write down the cross product. So, cross product of these vectors. So, you write down the cross product, it is I vector, j vector, k vector, del x del u, del y del u, del z del u by del x del v, del y del v, please follow the calculations, del z del v. So, if you know how to compute the determinant, what does this mean? This gives me determinant of this. So, what does this, if you look at the determinant of this, is del y by del u, del z by del u, del y by del v, del z by del v. It is a kind of Jacobian of the transformation. So, it is actually the determinant of, which I am not writing, I am writing it like this, determinant of this, which is same as writing determinant of del yz del uv I vector minus, now if you take j vector, then del x del z del x del z. So, it is del x del u del z del u del x del v del z del v. It is again the Jacobian of the transformation which you have learnt in change of variables. It is x z del u v is a determinant. And now plus, now this is into j vector plus, now the determinant you have to k vector. So, this row goes, this column goes. So, you are left with this part. So, del x del y del x del u del y del u del x del v del y del v. So, this is the determinant of del x y by del u v k vector. Now, if you look at the norm of this, you know what is the norm of this. The norm square, of course, is del yz del uv whole square plus del xz plus del uv whole square plus del xy del uv whole square. So, you know this is a norm square, the standard Euclidean norm. So, you know how this expression has now come, which is the root over the positive root of this. So, we have actually computed the cross product, but how does this cross product at all arise? That is the question that we are going to tackle in this discussion. So, how does this cross product at all would arise? So, Again we will talk about an infinitesimal area or an elemental area. I would always, I somehow call it elemental area, because that is a very basic building block, element, the element of an object, the basic element of an object. So here is my domain D. And here is my point UV, 2 dimension U and V. So here is the point UV, and I make a small change along this direction, that is U plus del U and V. Then I make a small change along both x and along this direction, but keeping the U fixed. So it is giving me U V plus del V, and then I have the last point where I make both a change along x as well as change along y. So these distance, this is my du, and this distance is dv. Infinitesimal distance, these are, infinitesimal is a very strange object in calculus. Euler said that it has to be 0. You want to talk really about infinitesimal. Infinitesimal means it is a small quantity, smaller than any quantity that you can think, any positive quantity that you can think. So it is a strange kind of notion, actually trying to talk about very small lengths or very small surfaces, Yeah, so or very small volume. So this is a this using very small quantities, very small things, is this is name infinitesimal got, you know, a kind of it got a it's a kind of lingo which calculus uses, and though there are you have a math for infinitesimals, but it is not so easy to comprehend them. But it is very important to understand that when some length is very small, so when del x is very small, the del x distance, the change in x, we shall mark it by dx. So of course this whole idea of differential is not so very clear. Maybe I should put a note. I have given a note to be given for Taylor expansion. So similarly I can put a note for what is the differential. This is something I think students should try to realize first. So many people, including Bertrand Russell, the great mathematician and philosopher, said that he found calculus logically sloppy. Does not matter, it works, it seems. But you know, the whole idea is that in the limiting version, see, calculus is a study of change, and not only a study of just a change, it is a study of continuous change, and calculus looks everything in the limit. So what happens in the limit is the question. How you are getting on and what sort of mental you know, conceptual ideas you are taking in to reach the limit is a secondary thought, but what happens in the limit is the key idea which calculus dwells on. And so now here we have, this is my domain D, sorry, this is my infinitesimal domain or elemental domain. This is the big one, is the domain D, elemental region. Now this by the map phi is getting into a 3D surface. I have a tendency to write or draw everything in the positive part, non-negative part. Does not mean you can draw it at any part, but it is easier to draw when you keep a drawing like that. Now here is a corresponding small elemental region, a kind of parallelogram, not really a parallelogram, something a little with little curved lines, that is there, that has formed here and this is your ds actually, the elemental area ds. So, how this form u and v is mapped here. So, this point gives me your phi of u v, this point gives me this one phi of u plus du and phi of u plus du and v. This point is mapped to the one here, this one which is phi of du. So, this point, this end point, sorry, which I have marked, not marked, I just wrote elemental region. This point here is actually u plus du and v plus dv. Carefully look at this, you should stop this thing and carefully look at the picture, stop the video. Here this point is phi of u plus du, v plus dv, and this point corresponds to phi of u v plus dv. So, I have been speaking about the area vector. So, the elemental area vector which should be perpendicular say at uv. So, this is my elemental area vector ds vector. So, this elemental area vector I can think of it as a cross product of these two vectors, which is, so they are cross product of phi u plus dv, cross product of these two vectors, that is, so I will the vector v1 which will be, so the ds vector will be the cross product of these two vectors v1 which will be phi of u plus du v minus phi of u v. So, here basically you are putting x of du, you are putting du plus du, u plus du. So, when you do a first order Taylor's expansion and forget about the errors, so what it remains, del x del u, del x del u this, du, del y del u du, del z del u du. So, I will just do that, and the v2 vector whose cross product I will also take, and that is phi of u v plus dv minus phi of u v. So, let us see. So, our ds vector, the elemental vector which is perpendicular normal to the surface, to the area, surface area. So, we are taking it as a, it is a minuscule zone. So, the straight lines, these curvy lines are almost straight because they are very small. So, we can talk about this as a kind of a parallelogram, not really rectangle, but a parallelogram. And so, essentially the cross product of the two sides gives me the area. So, the area vector now let us look at the v1, what is phi of u plus du. So, if you look at the phi of u plus du, that is x of u plus du j vector plus z of u plus du. Now, when v is fixed, all these x, y and z, these are function of the variable u, a single variable. When they are functions of a single variable, I can apply the Taylor's theorem, but I will forget the errors because du and dv are so small that I can forget the errors for all practical purposes. So, I can write approximately, I am not giving the equal to sign, please understand this. See, in the limit everything goes, the error vanishes in the limit, that is the key idea of calculus, the errors will vanish in the limit. This is the key idea, if you keep this in mind you will know calculus much better. So, you know, math has to be done also with some certain kind of intuition, it is not always that you are talking about rigor. Here of course we are trying to be quite rigorous here. And now here what happens is the following. Now here I can write this as a Taylor's expansion first order but forgetting the error. So it will be x of u v plus del x del u this I vector and similarly y of u v plus del y del u j vector. I am forgetting the del y del u du j vector. I am forgetting, I am just completely throwing away the error. That is why I am writing as an approximation, and it is a good approximation when they are very small. So z u v sorry y del u del z del u. I am sure if people were here they would have corrected. Now, now what happens if you look at this, if you take this as I, this and this, club them into one xi, yi, zj and this, then this one, then what I have got here is xuv plus phi u du, this vector. So when I am writing the v1 vector, which is the difference of this vector with phi u v, sorry this is phi u v, sorry not x u v, because x I plus y j plus z k gives me phi, and this plus this plus this would give me phi u, this will give me phi u vector into du, du is a scalar thing, a scalar into a vector. So what I would have when I write phi of u plus du v minus phi of u v, I will get phi of u v cancelled and this will become nothing but phi of u du. And similarly v2 vector by symmetry can be written as phi of v dv. So now when you are doing v1 cross v2, which is your ds vector, what you simply get is phi u cross phi v into du dv. So what I finally get here, that ds vector is phi of u cross phi of v into du dv. So these are norms, we essentially take them to be very small positive lengths, these are representing lengths, so we take them to be positive. So ds, the surface area, the ds, the elemental surface area which is the norm of the area vector, so is nothing but norm of phi u cross phi v into du dv, is positive quantities out of the norm. And so area of S is integral d ds, which is nothing but integral d norm of phi u. So, Taylor's expansion is the secret of many things in calculus. Please understand this thing du dv, and that is exactly what you want, and that is, and of course, you can make a more very strong expression, because you already know that this can be written as, because you already know this fact, thus this is del yz del uv, you know this already. You know that norm of this is what, I am just writing down what is the expression of norm in terms of our given data. Del of x y by del of u v. Sometimes I become quiet while writing, it might bore you a bit, but just bear with me, because I am also writing something pretty long. So, that is the expression. So, now once we have done that, a single example would show us that okay, what we have done is pretty okay, pretty decent. My Taylor's theorem game works. So, let us do a very simple thing. So, now let us consider a cylinder which is centered at 0, has a radius r, and has a height h. So, this is my z axis which is going through. So, this is, maybe my drawing may not be, this is also r. So, what is, you know what is the answer, of course, the surface area of a cylinder. So, basically if you cut through the cylinder and roll it off, you know that this one length side is nothing but 2 pi r, which is the circular circumference, into h, the breadth, length into breadth. Let us see where calculus can give us anything. So, how do I parameterize this cylindrical surface? I do not know whether it is, because for corresponding to every x y there is one particular z, there is a corresponding to every x y, here is a z. So, here is a corresponding to x y, here there are more than one z's. So, but they are not overlapping. So, I said that okay, we will not consider surfaces where one x y gives two z's, but I think that is not really the thing I wanted to mean. Means I wanted to mean that when you overlap across like this, then when the surface overlap on itself, then corresponding to every such x y you would have more than one. Here of course, you can say that I would have more than corresponding to any x z in the domain, right. So, where is what's my domain? My domain here is the circular domain. This circle is my domain, and of course, here I am having corresponding to every x, there is a more than one z. So, I cannot write it as a graph of a function, but see I can parameterize it. So, when I parameterize it, then that parameters will be r theta and z. So, corresponding to r and theta, given r and theta, there will be a particular z, that is corresponding to x, and corresponding to y there is a z. Actually, if you take any x y here, for example, take any x y here, on the surface of the cylinder all along this height h, where I have fixed x, y, the z's are part of the cylinder. So, they cannot be expressed as a graph of a function, but they do not overlap. So, I would like to rather correct my sentence, what I meant by that time, that I will not consider those functions which overlap itself, because overlapping will always give me situations where corresponding to one x, y, there are more than one z's, and because it overlaps there are issues of orientation and which we cannot handle. But when it does not overlap, but is not the graph of a function, we can still handle this situation using parameterization. So, what is my parameterization? Parameterization means x is expressed as a function of r theta. So, given an r theta there is a fixed x. So, given an r theta there is a fixed y, given a z there is a fixed z. So, for a r theta, for a fixed r theta there is no 2 x's or 2 y's, there are not 2 x, two different x y's, there are fixed x y's for a given r theta. So, I can now express what does parameterization do? One has to again remember at this stage that because I cannot express it as a graph of a function, because this surface does not represent a function, I can represent it in such a way such that its x coordinates, y coordinates, z coordinates itself can be represented as a function, and then we can apply our things by using this transformation, this kind of change of variable. So, we are making kind of a change of variable here, but so that my x coordinate, y coordinate, z coordinate which are not linked through some function can be linked through some parameters, and with respect to those parameters each of them are a function. So, that is the key idea, please remember this key idea. Here x is equal to r cos theta, y is equal to r sin theta, and z is equal to z. So, here my parameters are r theta, right. Here my parameters it's theta and z, because r here is fixed. So, I have been given a base of the cylinder which has a fixed radius. So, x and y will depend on the theta. So, if you give an input theta and z, sorry I am talking about r theta. So, if you give an input theta here, given input theta here, so for a given theta there is only one x, for a given theta there is only one y, not two y's, and for a given z there is only one z. So, theta z, for example here z is z theta z which is z. So, here also you can say okay, how do you express that as a function of theta, z and theta. So, it is z theta z and that is equal to z. That is what we are doing, that is the meaning of this. So, basically, so our parameters here are, our parameters are not r and theta, sorry, theta and z. So, r is fixed because the base of the cylinder is given. Our parameters are theta and z, right. The z is changing and theta is changing and nothing is changing. Now, if you go by what we have done earlier, so its area is given as, so theta is going from 0 to 2 pi, this is going from, z is going from 0 to h, root over. Now, we do those calculations. So, the determinant would be r cos theta 0, this is a thing given in the book, but you can just write others yourself, minus r sin theta, you are taking the derivative of cos here, 0, 0, 1 whole square plus minus r sin theta zero r cos theta 0 whole square into d theta dz, my parameters. So, if you calculate this, this will come up to 0 to h, 0 to 2 pi root over r square cos square theta plus r square sin square theta d theta dz. So, r this will just be r. So, I will take r outside. So, r times 0 to h 0 to 2 pi d theta dz, and this integration is now simple to you, r 2 pi h. So, that is 2 pi r h. So, calculus can give you get you back what you already know from geometry. Of course, you can talk about much more difficult looking curves. So, you can in fact also, for example, if you look at a surface. So, here is an example from the book, but I would like you to try it out yourself. Take a look from at the surface which is which is parameterized as homework. This is homework. So, before I end, I give a homework. X is equal to r cos theta, y is equal to r sin theta, and z is equal to r. So, your r and theta are your variables, right. Your r and theta here, your you parameterize by r and theta, parameters here are r and theta. So, now find surface area. The same story, same calculation, the same similar sort of calculation now you have to do with noting that r and theta is the same looking thing. Instead of z I have made here r is not fixed, here r is changing. So, you might try to get into your computers those you have and use MATLAB if you have and try to draw this surface and see what it looks. So, with this I end this talk here, and in the next class we are going to talk about how to integrate a scalar function over a surface, and then we will give a formal definition of a surface integral where we integrate a vector function over a surface. That is, instead of line integral f dot ds, we will have a surface integral, right. So, for a line integral you have done it over a line, over a curve f dot ds, where here their ds was the arc length, here so f dot d small s, that is what you have learned in line integral. Here you will learn in surface integral f dot d capital S, because it will talk about the elemental surface and they will talk about how to integrate that. That is, so integrating a vector function over a curve is a line integral, integrating a vector function over a surface is a surface integral, and that is what we are going to learn in the next class. So, after talking about surface integral, we will go to a second idea about orientation and all those stuff about surfaces, and then we will go into Green's theorem. So, which will be the last class of this 7th week, and then we will get into the 8th week, the last week, which will have interesting stuff.